Hi, good morning, everyone. Hope you're all doing well. So we're going to do a few different things today. We're going to look at a chi-square analysis. That's the last test on your agenda. So you may have already gotten to the lecture, maybe not, but we're going to talk about that today and work through an example together. Next, we're going to talk about the differences between all of the tests. Now, the bonus assignment was originally going to be due this Sunday. It's now due next Sunday, 5/9, okay? So that bonus assignment is worth 20 points wherever you need it, and it's all about the differences between the tests. So knowing the differences between the tests will be helpful on that, and will also be helpful on your final exam. Okay, and of course, even helpful on exam 3 for the test that we're covering on exam 3. You have to be able to know which test we're talking about sometimes in order to proceed with a problem. So helpful all around, I hope. And let's see, and then we'll just briefly talk about the general rules about hypotheses and when you reject and when you don't reject. So we'll briefly talk about that at the end. But that actually kind of covers some of what I wanted to share with you in terms of things to note in terms of due dates and all that kind of thing. So first of all, of course, exam 3 is tomorrow. It'll open at 5 a.m., close at 11:59 p.m. Don't forget your note sheet. It's worth 5 points. And just checking off that you did a note sheet is insufficient. I will go through and look at your note sheet. So make sure you submit a note sheet. And not just, has to be individually created, something you made, and put up there. Okay. So if you have any questions about that, you can chat them in or we can talk after. Then on Sunday, quiz 12, the last quiz is due. Okay, and that will be based on the chi-square. So listen to that chi-square lecture, and maybe what I shared today will be helpful in completing that as well. Okay, and then on, so you've got that. Then on, well, like I said, the bonus will be due the following Sunday, 5/9. One thing about class next week, okay? So assuming this class goes according to plan, which I think it will, then for next week, it's titled Pulling It All Together, and it's a red day. However, what I'm going to do is make it an open question session. Okay, I might have just a couple of quick things to say at the beginning, but it'll mostly be open questions. It'll be optional, but I will let you earn back an attendance you may have lost by attending. Okay, so if you missed an earlier attendance and you would like to make one up, you can do so by attending next Thursday. Then finally, your final exam, and that is cumulative, happens on Tuesday, May 11th. That's Tuesday, May 11th. So please don't let it throw you that it's a Tuesday as opposed to a Friday. I know Friday's been more typical for us, but it is a Tuesday. The rationale for that, in case you're curious, is I wanted to at least include the 2-hour time span that is assigned for this class. So if I made it on a Friday, for example, maybe you're booked all day Friday, I don't know. So I just went with what we were assigned for this class, but you won't just have the 2 hours, you will have from 5 a.m. until 11:59 p.m. You pick your time period to actually complete the exam, but it will be on the Tuesday, 5/11. So just emphasizing that so that you know that. Okay. If there's any questions about the admin pieces, please do chat them in. I'm going to start talking about chi-square now. And at the end, of course, I'll give you your attendance code for today. So again, any questions you have about any of those pieces I just shared, please feel free to chat them in. Okay, so you've probably noticed, actually, let me start my slideshow officially here. You may have noticed rock, paper, scissors, lizard, Spock, and hopefully that is familiar to you. Hopefully you remember that we actually looked at this at the very beginning of the semester when we were talking about frequencies. Well, chi-square brings us full circle because chi-square is all about frequencies. Okay, so we're going to take another look at rock, paper, scissors, lizard, Spock and determine frequencies, and from there determine our chi-square. Okay, so just to refresh your memory a little bit, and then I'll show you the video clip. And actually, let me make sure I share my computer sound or this won't go well at all. Okay.
I'll tell you what, how about we go rock, paper, scissors?
Ew, I don't think so. No, anecdotal evidence suggests that in a game of rock, paper, scissors, players familiar with each other will tie 75 to 80% of the time due to the limited number of outcomes. I suggest rock, paper, scissors, lizard, Spock.
What?
It's very simple. But scissors cuts paper, paper covers rock. Rock crushes lizard, lizard poisons Spock. Spock smashes scissors, scissors decapitates lizard, lizard eats paper, paper disproves Spock, Spock vaporizes rock, and as it always has, rock crushes scissors.
Okay, I think I got it.
Rock, paper, scissors, lizard, Spock.
Okay, so that is rock, paper, scissors, lizard, Spock. So let me highlight a couple of the really important pieces for you there. First of all, we did talk a little bit about rock, paper, scissors. Now, if you remember that game, the probability suggests that you would win a third of the time, you would lose a third of the time, and you would tie a third of the time. Now, the advantage of rock, paper, scissors, lizard, Spock is it reduces the ties. Now you're only likely to tie 20% of the time. You're likely to win 40% of the time and lose 40% of the time. So it's still a fair game because you win and lose at the same rate, but the ties happen hopefully at a less frequent rate. Now, the question that we might ask is, amongst friends, amongst people who know each other, will there be still more ties than we anticipate? Will it be higher than that 20%, right? Because maybe that's exactly what just happened with those two folks, right? They tied immediately, and maybe we can hypothesize, maybe that's because they know each other, they're more likely to tie than with people who, you know, the standard rates of 40%, 40%, 40% win, 40% loss, 20% tie. So let's talk about that a little bit. Okay, so let's say we want to conduct a chi-square using this. Well, the null hypothesis, and I know I rarely start with the null, but I am going to start with it today. The null hypothesis is that wins, losses, and draws are not different from the standard expected of 40% wins, 40% losses, and 20% ties. The alternative hypothesis would be that it's going to occur at different frequencies than the standard expected above. Wins, losses, and ties will occur with different frequencies than the standard expected above. Okay. Now, to get expected frequencies, what we would do is take our total N, the total number of games that are going to be played of rock, paper, scissors, lizard, Spock, and multiply by those percentages, the expected based on the null for each cell. So that's the next piece I want to kind of walk through with you guys. So we're not going to actually play the games, but we're going to look at some data where the games were played. So we're going to pretend that these games were played by pairs of friends who know each other. And so maybe their wins, losses, and ties will occur with different frequencies than the standard expected of 40, 40, 20. So Let's take a look. Let's say that 150 games were played. So similar to what we had done at the beginning of the semester. Let's say we had 10 pairs of friends, 20 people, 10 pairs of friends, and they each played 15 games of rock, paper, scissors, lizard, Spock. So 10 pairs of friends, 15 games apiece, 150 games total. So once we know our total number of games, we can get the expected frequencies. And how do we do that? Well, we take the 150 games that were played times that expected percentage that we talked about in the null hypothesis, 0.40. I should really say the expected proportion. I shouldn't really say percentage, right? Because we know percentage would really be 40%, whereas 0.40 is the proportion. Okay. So 150 times 0.40 equals 60 wins. We expect 60 wins amongst these 150 games. 150 times, again, 0.40, that's in the null, would also give us 60 losses is what we expect to see. And 150 times 0.20, that's for the ties, that's the expected for the ties, would give us 30 games that were tied. So we're expecting 60 wins, 60 losses, 30 ties. Okay. And I'm going to skip past these because we're not actually going to do this, but I mean, if they kind of talk through how you know who wins, and these were the 15 games. Okay, and now let's get into the actual calculation of a chi-square. Okay, so we already talked about the expected frequency, right? Total n times proportion expected for a particular cell, and that's what we already calculated. We have 60 wins expected, 60 losses expected, and 30 ties expected for 150 games. Okay, so how do we go from that to a chi-square? Okay, first thing I want to point out, this formula on the left with the FO and the FE, same, exact same as the formula on the right with the O and the E. So why do I present it both ways? Because you might see either one out in the wild. And so I just wanted you to be familiar with what it looked like. I didn't want you to be thrown if you suddenly saw one and we talked about a different one in class. But this one on the right is my preferred one. I like that it's very simple. It says observed minus expected squared for each cell, divided by the expected, and then add them all up. And we're going to go through this step by step. So as I note here, FO or O is the observed frequency, what we actually got in our data, which I'll show you momentarily. FO or E is the expected frequency. That's our 60, 60, 30 that we just talked about. And later on, we can talk about our degrees of freedom, which is C minus 1, where C is the number of categories. So we'll come back to the degrees of freedom. Let's first focus on getting our chi-square. Okay. So here's what happened. Actually, I'm going to take you out of here before you worry about the calculations too much. I'm just going to tell you 50 wins, 50 losses, 50 draws. That adds to 150, right? 50, 50, 50. So that's what happened. Okay, amongst these 10 pairs of friends who played the game each 15 times, 150 games, there were 50 wins, 50 losses, 50 draws. Okay, let's look at it. So how do we actually calculate the chi-square then? Well, we take the 50 observed minus 60 expected. That's negative 10. We square that, so negative 10 times negative 10 equals 100, because if you remember, negative times negative gives you a positive. And then we take the 100 divided by our expected, which was, again, 60, and we get 1.6667. Notice how we still hold on to our 4 decimals. How about losses? We also had 50 losses. 50 minus 60 equals negative 10 times negative 10 equals 100 divided by 60 equals 1.6667. So again, that's observed 50 minus expected 60 squared 100 divided by expected 60, 1.667. Okay, now we have ties. 50 minus 30, because this time we had 30 be our expected, equals 20. 20 squared equals 400. 400 divided by our expected of 30 gives you 13.3333. So again, that was observed 50, expected 30, squared 400, divided by expected 13.3333. Now the last thing, if you remember, I'll show you this one more time because I want to make sure it's clear. The observed minus expected squared over the expected, that's what we just did. Now what do we have to do? What's this little sign mean? Add them all up. So we're going to add up our 1.6667, our 1.6667, and our 13.3333, where we get 16.6667. Great. That's our chi-square. That's all we have to do to calculate our chi-square. Now we have to figure out if it's significant or not. Okay, how do we do that? So now let's talk about our degrees of freedom. Degrees of freedom, if you remember, is C minus 1, where C is the number of categories. So we had wins, losses, draws. 3 categories, or wins, losses, ties, whichever you prefer. 3 categories minus 1 gives us 2 categories. So DF is 2. DF is 2. 3 minus 1 gives you 2. So now we're ready to look at a chi-square table. Okay, and we're going to assume our alpha is 0.05. That would always be given to you. So alpha is 0.05. And remember, our DF is 2. So let's look at a chi-square table together. Alpha is 0.05. DF is 2. Our resulting number to beat is 5.992. 5.992. Now, since we're actually summarizing a little bit, let me just point out, I haven't mentioned a word about positive and negative, have I? Whereas I did before with the Z and T tables. That's because there's no negative with ANOVA, and there's no negative with chi-square. There are possible negative answers for z-tests and t-tests when we look in our table, so that's why we had to look there. You can get a negative correlation. You can get a negative regression coefficient. But for our F, for ANOVA, for our chi-square, it's always going to be positive. Those two are always going to be positive. Okay, so we don't have to worry about that. So 5.992 is our answer, is the number to beat, the number to beat. So is 16.6667 bigger than 5.992? Yes, it surely is. So there is a significant difference here. We can reject the null, and it seems to be the case that when friends play together in pairs, rock, paper, scissors, lizard, Spock, at least in this study, there were a higher percentage of ties, right? A higher number of ties that came out than what might typically be expected. So that's what we learned from this study. Okay. So again, it was significant because we beat the 5.992 and we rejected the null. Okay. And if you have any questions about this piece, please feel free to chat in and I'll be happy to address it. All right. So hopefully that offers a little bit of clarification about the chi-square. Okay, I'm about to show you a big table of tests. Now, if First of all, I just want to share with you, you do not have to scramble to write all these down. This has been posted for you in D2L under content, under comparison of tests. So again, it's in D2L under content, under comparison of tests. Also, if you like, I'm just going to go ahead and post this lecturette from today, lecturette, whatever you want to call it. I'm going to post it on YouTube for you guys so that you can review it later if you so desire. Okay. All right. So there's a lot of tests in this first table. Why? Why are there so many tests in this first table? Well, I'll tell you why. Because all of these tests have in common that they use one continuous variable. I don't know if you've caught that yet, but if you've noticed, all of these tests tend to have categorical independent variables and continuous dependent variables. Now, the other thing that's common about all these tests is that they're all designed to detect differences. So if you notice you have a test with one continuous variable, one continuous dependent variable, and you're detecting differences, you can narrow it down at least to this set. And that's a good thing. It's not a great thing, though, because there's still a lot of tests here. Okay, so let's work our way through them. Let's talk about how each one is different from the others, and that will help you be able to identify which test you're working with. Okay, so the z-test. This one's pretty straightforward because it's the only one where you know the population variance or you know the population variability. In other words, you're going to see a sigma. Sigma squared, sigma x bar, some form of sigma. Or it'll say the population variance is blank. The is what? Is 52. The population standard deviation is 13. The population standard error of the mean is 1.29. It'll give you this information. So some form of sigma, some form of population variability will be known if it's a z-test. So immediately, if you run into a problem and you see that you know a sigma, you know you've got a z-test. You don't have to worry about anything else. Okay. Now let's move on to the next one. Well, I should inform you that the z-test also has a known population mean, mu. Either it will say mu equals 30, for example, or it'll say the population average is 28 or what have you. But it'll say something about the population mean. So why did I not mention this a moment ago? Well, it's because the t-test for a single sample and the z-test have a population mean known. Both of those have this. So that's not a great distinguishing factor. However, the t-test does not have the population variance. So if we put these two facts together, you can know whether you have a t-test for a single sample. In other words, if you see a population average, a mu, a population mean, a population average, a mu, then it's one of these two tests, z-test or t-test for a single sample. If you do not have this population variance on top, in addition, I should say, it's a t-test for a single sample. If you do have the population variance, it's a z-test. So one other thing I'll just share with you about these two tests is that they both compare a sample to a population. They both compare a sample to a population. So if you notice that that's what's going on, we're looking to see if the general population average is different from the sample I collected that has an average of this, you know you're down to one of these two, z-test or t-test or single sample. And again, you will see that population average for both. And if you, in addition, see the population variability, z-test. If you don't, t-test for a single sample. Okay, enough about those two. Now let's move on to t-test for dependent samples. This is the only test where people are tested twice. It's the only test where people are assessed or tested twice. Okay, 2 values or scores per participant. This test, t-test for dependent samples, is extremely similar to the repeated measures ANOVA, because that's the only test where we test people 3 or more times. 3 or more times. So let me give you a couple of examples. T-test for dependent samples. I look at people's blood pressure at the beginning of the semester and at the end of the semester. T-test for dependent samples. I tested them twice. Now for repeated measures ANOVA, I look at people's blood pressure at the beginning of the semester, 4 weeks into the semester, 8 weeks into the semester, and at the end of the semester. Repeated measures ANOVA. I tested them 4 times in this case. Could have been 3, could have done beginning, middle, and at the end of the semester. That would be fine too. Still would be a repeated measures ANOVA. Let me give you another example, because I think we tend to look for always the beginning and the end, or pre and post, and I want you to be open to other ideas. So for t-test for dependent samples, another example would be, I'm going to put you in a simulator, driving simulator, and one time you'll have a phone and another time you won't have a phone. Still tested you twice, right? One time with a phone, one time without a phone. It's a very bad study, because once you get practice in the driving simulator, you'll probably do better the second time. But let's not worry about that. Let's just focus on the fact that I put you in the driving simulator twice, with a phone, without a phone, 2 different conditions, put you in there twice, still t-test for dependent samples. Now I'll put you in the driving simulator 3 times. One time with a phone that's handheld, one time with a phone that's hands-free, one time without a phone. Repeated measures ANOVA. Notice I tested you 3 times. Okay. Okay, now let's move on to the t-test for independent samples. This is when you have 2 completely independent groups of people. No overlap. For example, I want to compare people in my treatment group and my no treatment group. Or let's say I want to compare people in psychology who have a psychology major versus people who have a math major. Now there I could run into a little bit of a problem, because let's say someone has a double major in psychology and math. What do I do with them? Well, they simply don't qualify for this study because they can't be in 2 categories. The categories have to be independent. Now, this test, t-test for independent samples, is very, very similar to the one-way ANOVA. Very, very similar to one-way ANOVA. In fact, the only difference is 2 groups for the t-test for independent samples, 3 or more groups for the one-way ANOVA. So now maybe I have a waitlist control group, or just a control group that I'm doing in my treatment. And then I have one group that's getting cognitive behavioral therapy and another group that's getting interpersonal therapy. 3 groups, 3 independent groups. Or if we would like our major example better, let's say I have psychology majors, physics majors, and math majors. And no double majors in there, or triple majors, because we can't have people from more than one group overlap. Right? So if someone was a major in psychology and physics, they would not work for this study. Okay. And this again can be 3 or more groups. So we can add in sociology here. We'll have psychology majors, sociology majors, physics majors, and math majors that we'll compare and see if they're different in terms of their overall happiness with their academic program. Notice that continuous variable, happiness. Okay, so that's the one-way ANOVA and the t-test for independent samples. Okay, so all we're left with at this point is the factorial ANOVA. Factorial ANOVA, what makes this one unique? Two independent variables, and I should say really two or more independent variables. We're not only going to look and see if major impacts happiness, but we'll look and see if living situation impacts happiness as well. Whether or not people are living in a dorm or off-campus housing, or living with relatives or caregivers. We'll look at those three groups. So, and we could look at two groups. We could just look at on-campus, off-campus living, right? But we're looking at two independent variables to see if they impact happiness, both major and living situation. And notice both of those variables are categorical, whereas the happiness is continuous. There's our one continuous variable again. Okay. Factorial ANOVA is also the only one where we can look at interactions. So maybe an interaction, let me give you an example of an interaction. We'll keep it simple. Let's just keep it to psych majors and math majors who either live on campus or off campus. Okay. Let's say psych majors who live on campus are happier, but math majors who live off campus are happier. So then if I asked you the question, well, which major's happier? You'd have to say, well, it depends on whether they live on or off campus. And if I asked you, well, which living arrangement makes students happier? You'd have to say, well, it depends. It depends on whether they're a psych major or a math major. Okay. All right. Enough about this group of tests. Let's move on. And this was the biggest group, so the rest are smaller. Let's move on to our next one. This is the one with two continuous variables. Two continuous variables, right? So we looked at number of hours of sleep and happy mood or happiness. Both are continuous. The other thing that's unique about these tests is that they look at association, if it's the Pearson correlation coefficient, or association and prediction, if it's simple linear regression. Now, a really important difference between these two is that the IV and DV, the independent variable and dependent variable, are not defined for a Pearson correlation coefficient. And what do I mean by that? You could mix them up. Is sleep associated with happiness? Is happiness associated with sleep? You could ask it either way. Doesn't make a difference. Whereas with simple linear regression, it is defined. We would say that we want to know if number of hours of sleep obtained per night predicts happy mood ratings. So the thing is, it may not always be easy to see in a word problem whether or not the IV and DV are defined. So here's my big hint about word problems. Look for the word predict. You've got two continuous variables. You're trying to decide between Pearson correlation and simple linear regression. Look for the word predict. If it says predict or predicting or predicted, you've got a simple linear regression. If it simply says associated, related, you've got a Pearson correlation coefficient. So that's the best way in the word problems for this class, for these tests, to tell the difference between Pearson correlation and simple linear regression. Okay. So again, first thing you're checking, how many continuous variables I have, figure out which one of these tables you're in, and then you can go on and figure out the rest. Figure out which actual test you have. Okay? Okay. All right. One more to go. This is what we just talked about today. Chi-square. Now, this is when you have 0 continuous variables. In other words, everything's categorical. Everything's nominal. Now, we've only talked about the chi-square test for goodness of fit, and that's the one you'll notice I really emphasized in the lecture. I just want you to understand the basic difference between these two, but we're not going to get into the calculation for the chi-square test for independence. Now, they're very similar. What's different between the two? Well, one nominal variable, two nominal variables. So the example we just looked at was a one nominal variable was chi-square test for goodness of fit. Did you win? Did you win? Did you lose? Did you tie? Okay, chi-square test for goodness of fit. Now, let's say we wanted to look at another variable along with win, lose, or tie. What else might influence, or what else might be interesting to look at in addition to whether a person wins, loses, or ties? We could look just for fun at trying to come up with a great example for you guys, at favorite color. Okay, so, and we're only going to give people two choices. You have to choose between blue or red. What do you prefer, blue or red? Because maybe in the world of vast literature out there, there's someone who hypothesizes that people who prefer blue have a higher number of ties, and people who prefer red have a lower number of ties. So we could see if the proportions are different for win, losses, and ties amongst people who prefer blue as compared to people who prefer red. Okay. All right. So only difference between these two is one qualitative nominal variable, two qualitative nominal variables. Okay, and that's, in terms of chi-square test for independence, that's the only thing I need you to know, really, is what it looks like. Okay. All right. So that brings us to the end of the table section. I have one more piece I want to share with you. And if you have any questions as I'm going through, please feel free to chat them in. Okay, this is statistical test interpretation, as I promised. Now, first, we're going to talk about hand calculation. Okay. Now, if you remember, I didn't have you do hand calculation for ANOVA, for the F statistic. I didn't have you do hand calculation for the correlation, the R, or for regression, which is also an F statistic. Okay. So let's just talk about the ones where we did do hand calculation, which is the z-tests, the t-tests, and the chi-square tests. And what we're going to say is if the calculated z, t, or chi-square is more extreme, more positive, or more negative than the tabled value, the result is statistically significant, and we're likely to reject the null. Okay, so let's break this down a little bit. ZT can be positive or negative, as I just shared with you. So we're looking to see if it's more positive or more negative. Chi-square and ANOVA F tests will always be positive. So there we just started looking if it's more positive, if it's bigger. But either way, we're trying to beat what's in the table. What we calculate, what we get by hand, we're trying to beat what's in the table. Okay, and if we do, it's statistically significant, we're likely to reject the null. If we don't beat it, that's easy. The result is not statistically significant and we do not reject the null. So why this likely? Why am I hedging my bets here? Okay, if you remember, this comes down to whether it's a one-tailed or two-tailed test. If it's two-tailed, you're done. Result is statistically significant, you'd reject the null. But if it's one-tailed, there's one more thing you have to check. And that's if you have a one-tailed test and the results are in the opposite direction of what was predicted in the alternative hypothesis, you don't reject the null. In other words, if I said math majors will be happier than psychology majors, but it turns out psychology majors are happier than math majors. Doesn't matter what kind of finding I get, I'm never going to reject the null. It could be really statistically significant. I'm not going to reject the null. Okay. Now let's talk about SPSS for a moment. Okay, we talked about hand calculation, now SPSS. And SPSS we did for everything, right? Z, T, ANOVA, correlation, regression, and chi-square as per your lecture. Okay. So here, the good news is it's always the same. It's not a bunch of different tables. You're always looking at the p-value or sig value. Now, if the sig value is less than your alpha, and alpha is always given to you, the result is statistically significant and we're likely to reject the null. If the observed p-value is not less than alpha, not statistically significant, don't reject the null. So again, I'm hedging my bet with the likely there. Why? Same reason. If it's two-tailed, you're done. If it's two-tailed and your p is less than alpha, your result's significant, you reject. But if it's one-tailed, the result may be statistically significant if p is less than alpha, but if it's one-tailed and the results are in the reverse direction of what you predicted, you're not going to reject the null. You're not going to reject the null. Okay. Finally, let me just add in one piece since we're kind of reviewing and talking about things. Remember, SPSS always gives you sig values for two-tailed tests. So if you need a one-tailed test, what do? Take that sig value, take that p-value, and divide by 2. Divide by 2. That will give you your one-tailed sig or p-value. I know it's a little counterintuitive, but that is how it does work. Okay, so you take that sig or p-value, divide by 2. Don't change your alpha. Don't change anything else. This is the only thing you need to worry about is your sig value or p-value that you're dividing by 2 for a one-tailed test. Now the rule still applies. If my prediction's wrong in that one-tailed test, I'm not going to reject. Okay. Still good to know the actual p-value, but I'm not going to reject. Okay. So that's what I wanted to, and this is our exception again that I talked about. So remember, one-tailed, results are opposite, don't reject. Okay. That's the main stuff I wanted to talk to you guys about today. I'm going to give you the attendance code in just a moment, and I will invite, as soon as I do that, I will invite anyone who wants to stick around and ask additional questions or chat about anything to please do so. Okay.